I suggest we start. I think that some people will come up in a while. But first of all, good afternoon, everyone, and welcome to a webinar organized by the Graph-Massivizer project. My name is Nuria Delama. I'm Consulting Director at IDC, and I'm really honored to present this webinar today. First of all, I would like to give thanks to our colleagues from HIPEAC. Thank you very much for giving us the opportunity to organize the session in the context of HIPEAC, which is a very interesting community to us. And also thank you very much to all my colleagues because they have made a big effort in preparing amazing content. So I hope that the audience today will really appreciate these efforts and you will enjoy the contents. Let me share also some important things for today. We will record a webinar so that people can rewatch the content, and especially for those that are not able to come today. If any of the people attending the webinar has any issue about that, please let us know. And then the second thing is some housekeeping rules. It's very important that if you are not speaking or you are not intervening in the webinar, you please switch off the camera, apart from our speakers, of course, and please stay muted so that we don't have background noise and it is easier for everyone to understand what our colleagues will share with you. Then you may see on your screen that there are several options to make questions. So please use the chat option when you want to share some comments about the content that we are sharing here, and also if you have any question. You can also use the option of questions and answers that you will see besides the chat, especially if you want to address any specific question to any of our speakers. But in principle, if you don't have any problem with the functionality, I suggest we all use the chat because this will allow people to see what other people are already posting. I think it will be easier to follow up the different comments and to come up with answers to those ones during the webinar if time allows. I think that's the most important thing I wanted to say. If I don't forget anything, let me share my screen just to provide a very brief intro to the webinar. And then I will give the floor directly to our project coordinator. So again, welcome to this webinar where we will be addressing mainly topics of the Graph-Massivizer project on graph processing. As mentioned, sorry, I think you don't see in presentation mode. Here it is. So you don't need to register anymore because if you are here, that means that you already registered. We have elaborated a quite packed program. Let's see if we have the time to go through that today. But first of all, what we want is to provide a general overview of the Graph-Massivizer project. There are many challenges around graph processing of extreme data, so you will understand a bit better how to use these technologies, what are the challenges nowadays, and what are the contributions that the Graph-Massivizer project plans to do and is already doing. So for this, we have invited our project coordinator, Radu Prodan from Klagenfurt University, and he will really provide a very comprehensive overview of the project so that you can understand also the things that come a bit later. Then, since the project is quite ambitious and has a lot of different working areas, we decided to select specifically two technical presentations that could be of high interest to the HIPEAC community. So they are especially selected for the attendees today. One of them focuses on how to run these technologies on the computing continuum, since we understand that there may be people here representing high performance computing and other computing technologies. So we thought that this could be a nice element to talk about today. And then also because of the relevance of the topic, we will have another presentation by our colleagues from Chineca, more focused on the energy awareness and sustainability of magic graph processing. So this is just a partial view of the technical activities the project is doing. But again, thanks to Radu's presentation, you will get an overview and you may be able to join future webinars later on if you are interested in the technology. Then we thought that it would be a bit boring just going through theoretical concepts. And we thought it would be quite interesting maybe for the audience to see the way technology can be put into practice. And for this, we have invited our colleagues from University of Bologna to present one of the amazing use cases we have in the project. And this is interesting. Let's see how it works. But you will get both a presentation, but also a demo. And so like this, you will be able to see the kind of things we are doing in the project. And then in order to make this a bit more dynamic, we will run a panel discussion that will be moderated again by Radu, the project coordinator of Graph-Massivizer. And here you will be able to expand a bit the knowledge about what we are doing in the project, because beyond the use case that will be presented by University of Bologna that is executed in collaboration with Chineca, we have invited the people that are leading the other use cases in the project. And our main objective with this is that you see the way all these technologies that we are developing here could be used in completely different operational environments in order to address specific challenges of either economic or societal nature. And with this, we will close the webinar, and I will provide some instructions and next steps so that you can stay tuned about the project and come with us to the future events and activities that we will be doing in Graph-Massivizer. So as mentioned, we have an amazing set of speakers today, but since we don't have a lot of time, and as I mentioned, the program is quite packed, I would like to give the floor directly to Radu Prodam, coordinator of Graph-Massivizer from Klagenfurt University, so that he inspires us about the content that Graph-Massivizer is producing. With this, I close my screen, and then Radu, the floor is yours. Thank you very much for being here with us, and let us know about Graph-Massivizer. We see it, but not in presentation mode.
Yeah, I was looking for
sorry, yeah. Thank you for the HIPEAC colleagues. They are reminding me about a poll. Maybe just before we start with this, I would like the HIPEAC colleagues maybe to launch a poll so that we understand who is familiar with graph processing technologies, and also to understand if you know about Graph-Massivizer project before we go for that. Okay, let's see. This will allow us also to understand what is the level of knowledge of the people connected here today. So I see that most people know already about graph processing, and there is more or less half and half that know about the Graph-Massivizer project. Okay, so this is already good knowledge for our colleagues. Let's try to explain things so that they are suitable and useful both for a project community, but also for people from outside. Thanks a lot for launching the poll, and sorry that I forgot about that. And now, finally, Radu, the floor is yours.
Yeah, the screen is mine. So I'm the coordinator of Graph-Massivizer, and I will give you a short introduction about our goals. So it's a 5 million euro project. We started in 2023 in January, and we have 12 partners that you can see here. So we run basically in the data unit, extreme data mining, aggregation, analytic technologies and solution RIA unit of the European Commission. So before my colleague will overload you with technical information, I thought let's go, basic. Let's start with the basic history. So graph processing has a long history. It started basically almost in the Middle Age, right after. So the 7 bridges of Königsberg, this was a problem solved by Leonhard Euler. The idea was the following. So there is this old city of Kaliningrad in Russia now, called Prussia. And the problem was how to find a route, a path, a walking path through the city that crosses all the streets, but also gets to the 2 main islands that were on the city and connected to the mainland through 7 bridges. And Euler made the first analytics on the problem, and he reduced the problem to a simple or complicated at that time graph processing problem. So his rationale was that the cities are irrelevant, the bottleneck is relevant. So we have the 2 islands here and the mainland, and we have the 7 bridges, and how we can traverse this new graph representation in a way that we traverse every edge only once. And then he built an algorithm for that, and his rationale was the following. So to traverse the islands, you basically need to enter and exit the island. So you need 2 bridges at least if you want to reach an island, while for the mainland, it's enough to just enter or exit. So from that point on, he defined what we call today an Eulerian path in a graph. So a path that traverses a graph, each edge of the graph only once. And the property is that the inner nodes have to have an even number of edges touching them, what we call degree. So even degree for the inner nodes, while for the start and end nodes, this can be flexible. You can just touch them once. So basically, this is a property that is necessary and is also proved to be sufficient for the graph to be traversed. And we see in this figure that this is not the case. So the inner nodes have an even number of edges, 3 and 3, and also the start and end node. So this problem basically was proven by Euler to be unsolvable. So it's impossible to traverse Kaliningrad by traversing at the edges only once. So starting from Euler, things progressed, but that time things were much slower than nowadays. So it took about 100 years until Kirchhoff defined the fundamental laws of modern electrical circuits and engineering, combining graph theory with computational technologies. Nowadays, we have computer science. Yes, so we come from mathematics. The mathematicians like Euler invented statistics and data science, what we call today. And with the help of computer science, we reach a community that we are trying to establish in Graph-Massivizer, which we call scaling data. So scaling data means the ability to conduct analytics on data. Graphs are a representation of data that basically does not change in complexity of achieving it. And of course, with the help of computer science, this is the challenge that we are trying to solve together. We call also big data, extreme data. In Graph-Massivizer, we say scaling data. So from the 5-node graph of Euler, we move today with the help of computer science to massive graphs. Some examples, for example, social networks, the biggest application worldwide, connecting billions. I think over 4 billion of people use social networks today. So you have billions of vertices and 100 billions of connections. Of course, the web, it's another big graph, over 15 billion pages, 1 trillion of hyperlinks. And the holy grail that we have in science today is basically to simulate the brain network with over 100 billion of neurons, 100 trillion of connections. So basically, this is the scale that graph processing is striving nowadays. Now, if you look at the existing technologies out there, a lot is available. And what we are doing in our community systems community is to establish referent architectures. We started from data center. So that's why we are here. We are in HIPEAC, where systems, high-performance computing is in the center. And we have this protocol stack that defines it. We try to map graph processing on top of the data center software stack. And we saw that it matches a lot. It matches a lot. And what changes is a little thin layer here that deals with high-level languages and representations of data. So a lot is out there, but we miss a consolidation. That's what we are trying in Graph-Massivizer. So we want to have a project that automates the massive graph lifecycle, starting from data ingestion and graph creation, so streaming of data and on-the-fly creation of graph. On top of the streaming graph, we want to have complex analytics and reasoning algorithms. So these are on the graph application side, while on the system side, we want to automate the entire processing efficiently with workload modeling at the high-performance computing level, with energy awareness and sustainability at large scale, plus scalable graph processing using modern serverless technology. We will have talks today on the serverless area and on the high-performance computing area, including some of the use cases. So basically, some of the challenges that we try in our project related to the data are volume. So try to scale these graphs up to billions of vertices and trillions of edges with scalable analytics. The velocity with dynamically changing topology based on streaming data. And we also have a new V, what we call viridescence, is to fulfill graph processing analytic as a sustainable scale, using, of course, green processing technology. What we promise in the project is to have a Graph-Massivizer toolset. It's a set of tools. So it consists of basically 5 tools that operate at 2 layers. At the operational layer, we have the Inceptor tool, Graph Inceptor, that deals with data ingestion, massive graph creation and storage. So how to perform these activities on the fly. On the Scrutinizer, we deal with analytics and reasoning. Here we also target things like graph sampling, graph summarization, so how to scale down massive graphs so that we can still perform accurate analytics on them. So these 2 tools are on the front end, on the graph operational side. Probably in this community of HIPEAC, we are more interested in the back end, where we have a combination of 3 tools. So let me also say the involved partners of the Graph Inceptor. We have Josef Stefan Institute and SINTEF. For the Scrutinizer, we have Vrije Universiteit Amsterdam, and Joseph Stefan Institute as well. For the Graph Optimizer, it's University of Twente in Netherlands. So here we deal basically with understanding better graph workload based on basic graph operations, so how you decompose such workflows in operations, and how to basically configure customized hardware that runs at a better efficiency for such difficult algorithms that are graph algorithms. We know that existing high-performance computing systems are designed for dense linear algebra problems, which is different than graph processing problems. Graph Greenifier scales the optimizer at a massive level, at a global level, where basically we need simulation techniques and sustainability methods. What we are trying, among others, is to have a labeling on graph algorithms like household appliances A, B, C, and D based on their energy friendliness. And choreographer, we will have a talk here. It's basically the scalable execution of mathic graphs over the computing continuum. So we will also try to decentralize the entire execution from the central hotspot of the high-performance computer to the distributed edge fog continuum ecosystem. As use cases, we'll have a panel of them. We have 4 use cases. All of them target the 3 pillars of sustainability: economy, society, environment. I will not talk about them. I will let the panelists introduce them. Briefly, green and sustainable finance targets, of course, finance by excellence is economic, but we also want to invest in green bonds. So we also target environmental impact. Global foresight for environment protection. Here is a use case that tries to influence policymakers for better global foresight regarding the United Nations sustainability goals. In the first use case, we have Peracton from Ireland. In the second, for global foresight, we have Event Registry from Slovenia. Green AI for sustainable automotive industry, it's Bosch. So here we want to have to automate their product pipeline regarding the body-in-white construction of cars using green artificial intelligence techniques. And finally, the highlight for this webinar is a data-centered digital twin for sustainable exascale computing, piloted by Cineca University of Bologna. So basically trying to understand the interconnection between workloads, operation of the data center cooling system at the exascale level, using, of course, also anomaly detection techniques. So how to scale a supercomputer at the exascale in a sustainable way. And I'm finished. Thank you very much for the paying attention to my introduction. And I think now I will give the screen to the next speaker, who is Reza, that will present us serverless choreography part of the program.
Thank you, Radu, for the comprehensive overview. Just before we go on, someone put a question there saying that the chat function doesn't work. So if you feel that that doesn't work, please include your questions in the question and answer facility, and I will be checking them and informing our speakers about them. Then also someone else asked about the presentations. Presentations and the recording of the webinar will be available. So I will tell you where to go after the webinar, okay? So don't worry about the materials. You don't need to record anything. We will make everything available. Thanks a lot. And with that, we go directly to Reza. Thanks a lot, Reza.
Thank you, Nuria. Hi, everybody. I'm pleased to present today about a scalable and sustainable serverless graph processing system. So thanks to Professor Prodan's presentation, right now we have comprehensive overview about graph processing. Graph processing nowadays is spread everywhere about all use cases like data centers, like security, cybersecurity, social media, and with increasing the nodes, also the edge of each graph, even the resource utilization and energy consumption is the main challenge for such type of applications. So in Graph-Massivizer project, including 12 partners, we focus for extreme and sustainable graph processing for urgent social challenge in Europe. So today I would like to just focus for serverless computing aspects of that and introduce our tool called Graph Choreographer. As you know, imagine a scenario you just want to run some application as a developer over the cloud computing. In traditional one, you have to lease an instance over AWS, for instance, cloud provider, or Microsoft Azure. You have to always take care about its maintenance, scaling up, down, and even in some cases, you have to pay money without using any instances in idle time of your usage. But serverless computing just emerged to solve such type of problems and challenge by just dividing problem into two parts, one of that application part, another part for the infrastructure. Regarding the application, you don't need to always take care about the maintenance of the infrastructure, just focusing on your application, dividing it into multiple functions, and then triggering your function after deployment, and think about, the performance of your application, and the charging model is completely changed based on your usage. So nowadays, all public cloud providers like AWS, IBM, Azure, Alibaba, Google, provide such type of services. And statistics shows that even the number of organizations using serverless computing increased potentially in these years, and even by supporting such type of container Docker, paradigms, Microsoft Azure, AWS, and even potentially Google Cloud usage increased in terms of serverless computing. But think about a complex problem. So nowadays, complex application includes more function. I mean, more than 1-2 functions in a DAG representation. I mean, direct acyclic graph. Usually, connected into sequential, parallel loop, no operation, and many different, functionality as a serverless function. So what will happen for such type of application and serverless platform? So even for this problem, for DAG processing, workflow processing, public cloud providers like AWS, Google, Azure provided, specific services like a step function, but their platform is not dedicated for graph processing. This is the main challenge for our project, and we just wanted to use not only cloud computing but also edge computing for solving such problems for graph processing, dedicated for graph processing. So even some public cloud providers always, using such type of providers, always developers, application providers encounter some vendor lacking, problems. Imagine just developing something for Google, GCP cloud provider, or even AWS, but just for migrating or using a federated cloud provider. Again, they have to spend many efforts and times for such type of development. So of course, there are some dedicated graph platforms like Graph or GraphX, but they are not take care about sustainability concerns, also resource utilization, and they are limited to a specific amount of instances and resources. So this was the main motivation in Graph Choreographer, also the whole Graph-Massivizer project. We think about heterogeneous environments of instances of hardwares in different layers, like edge devices super close to the client side, the application developer, fork nodes in close to the base station, like G-Node B in 5G literature, or even traditional cloud providers, and equip them with serverless capability, and using such type of heterogeneous environment as the edge cloud continuum, and even using some HPC servers with more computational and storage powers. So as Professor Prodan talked about our conceptual Graph-Massivizer architecture, we have 5 layers or 5 tools, including multiple parts. So here in this presentation, I just focus for Greenifier, also Choreographer for addressing the sustainability, also the serverless aspects of graph processing. Imagine we receive a graph, a raw input graph. We just need to run some we just need to make it as a graph representation, raw input data into the graph representation, and then after finding some useful information about that regarding the profile, also the cost, the resource utilization, we need to run our scenarios as a function, as you can see here, like basic graph operation divided into multiple parts, and then applying some techniques like scheduling, like provisioning, like allocation for just dedicating, also distributing such type of task of graph processing on over the computing continuum. It could be our public cloud providers or fog providers, or even some limited resources like Raspberry Pis or Jetson Nano. So this is the initial architecture of our graph choreographer, and we just try to develop function by function, also workflow by workflow for such type of graph processing. So we encounter many challenges, and we just try to address step by step this research question. The first one is how to design a scalable workflow management system for graph processing, dedicate that for graph processing application. The second one is the serverless computing continuum, and we just need to design such type of continuum, equip that with serverless function as a service capability for broad class of graph algorithms, and how it's possible to consider not only the performance but also the sustainability aspects of graph processing algorithms. And finally, we just need to have some estimation, some prediction, and creating a serverless digital twin for applying algorithms over, also running some algorithms, graph processing algorithms over computing continuum. So there are many state-of-the-art and challenges. For instance, how is possible to increase the number of runtime code over the computing continuum. The next model could be codeless or deployless, or even how it's possible to use CPU, GPU, heterogeneous environment of resources, computational resources, storage resources, etc. So we are in this tool just try to answer such type of question. Thank you so much for your attention. I will be happy to answer all of your questions in the panel.
Thank you very much, Reza, and very good in terms of timing. So you organized the presentations very well. I would like just to check if people can see my messages on the chat. Is that okay? Can you see them? Just to be sure that if any of the attendees has a question or a clarification or a comment to make, that the tools are working properly.
I can see.
Okay, perfect. Thank you very much for the confirmation. Then let's go to the second technical presentation of today. Yes, I think this one addressing the sustainability aspects and energy awareness, which I think are hot topics nowadays for any organization, even more in this context. So let's go with our colleague from Cineca. Matteo, the floor is yours.
Yeah, thank you, Nuria. I share my screen. Okay, you see my screen in presentation mode, yeah.
Perfect.
Okay, so thank you, Nura, and welcome everybody. I am Matteo Anginelli and working in the data analytics group of the high performance computing department in Cineca here in Bologna. And today I would like to talk with you about the use case of the Graph-Massivizer project in which Cineca and University of Bologna are involved. And in particular, just to give you an introduction of the reason why Cineca and University of Bologna are working on this project, we need to talk about the energy awareness and the sustainability of massive graph processing. Yeah, to talk about that, we have to, first of all, introduce the problem. So the problem, we can look at the problem in two different aspects. The first one is related with the hardware component of a data center. In particular, this is related with the fact that the hardware component in modern data set are made by using fossil fuels, and also are made by rare metals that are non-renewable resources. And this is a quite huge problem for our society. But also another problem of the hardware component of a data center is that due to the modern technology, our hardware are suffer for a very rapid obsolescence. And if we look, for instance, at the image in that slide, we can see how the amount of tons of electric waste generated per year in the entire world rapidly increase in the next few years. So we have to take care about this problem when we talk about the data center. Another important aspect is the energy consumption of the data processing. Indeed, this is not related only on the evaluation of the impact of the data center in the energy consumption, but is a more related problem to the entire processing of the data processing in our society. Indeed, if you look at the images on the right side of this slide, we can see how the data centers in the world have an energy consumption that is completely comparable and even more greater than some country in the world. So we have to take care about the energy consumption of our data center. Indeed, if we look at more, if we try to give some number about the energy consumption of data center, we can see how the data center are responsible for about 1% of the whole energy consumption in the world, and this is also translated in a generation of about 1% of the greenhouse gases, and this is a very huge problem because our society is based on data, and processing the data is necessary for our future. So we have to consider also this aspect in our analysis. But if we look only at the data center, we have also to take care about the water consumption. Indeed, a data center to work properly and in an optimized way have to work in a constant temperature. So the room in which the supercomputer are located have to work in a defined temperature. And to maintain this temperature constant in often or more or less in each one of the data center, the way to maintain this temperature constant is to use water for cooling. But this is also a very another impact. This is also has an impact in the energy consumption of a data center. So we also have to take care about that. But why Cineca and University of Bologna are so interested in these topics? So since the beginning of this year, Cineca hosted one of the most powerful supercomputer in the world, which is Leonardo, a pre-exascale supercomputer, which is composed from two different modules. And in particular, the booster module, which is composed by more than 3,000 nodes, is particularly useful if you want to develop artificial intelligence and deep learning algorithm, because each node of this booster module has also 4 different accelerators. So in principle, it has also 4 different GPUs, and this is particularly important. And the GPUs are fundamental to develop and to become faster our algorithm when we study artificial intelligence. And this is one aspect of the Leonardo supercomputer, but it's also interesting to look at the energy consumption of Leonardo, because this is the topic of our use case in that project. So if we look at the energy consumption of a supercomputer like Leonardo, which is a pre-exascale system, when this supercomputer is in a full operational situation like the one in these days, Leonardo consumes about 6 megawatt. And this value is completely comparable with the amount of energy needed by a small city of about 20,000 people. So it's interesting to have a comparison between a supercomputer and something more familiar with all of us, which is an amount of people. So, and this is the reason why we are interested in the problem. But how we can address the problem? How we can mitigate or address to that problem? So, in the Graph-Massivizer project, Cineca, together with the University of Bologna, are working with the data center digital twin for sustainability exascale computing use case. And the scope of this use case is to develop a digital twin of the Leonardo supercomputer But this digital twin is not only an instant monitoring system for that computer, but this allows us also to have prediction and to prevent some anomalies and some failure on the compute node, which is fundamental to optimize the uses of the resources. But of course, we want also a digital twin that allows us to make some simulation to prepare ourselves for the next generation of the supercomputer, the exascale generation of the supercomputer. In order to assess this important goal, we decided to combine the powerful of the graph with the tools developed by the University of Bologna, which is the hexamon monitoring system. We want to use graph because graphs are naturally able to manage and understand the complex interaction in the system, and a data center is a very complicated system because we go from very small objects such as GPU and CPUs, but we have also very huge systems such as the cooling system. So we have a wide range of dimensions of the system which are all interconnected, and we have to understand very well the interconnection between this system. But to do so, we also have something that monitoring different systems, and we use the hexamon monitoring system. This monitoring system developed by the University of Bologna and already installed in the Cineca machine are able to take track all the components of a data center. So we have some plugins that are able to monitoring the GPUs, something for the GPUs, but also for the cooling system. So this allows us to have an holistic view of a supercomputer data center. Okay, now we have the tool, we have the idea, but what are our goals in that project? So mainly we can divide our goals in two different aspects, very challenging, but very interesting and very important for us. The first one is related with an improvement of the users of resources, because of course, if we better use our resources, we have more power to use in many different projects. And to do so, we necessarily have to be capable to prevent, to predict and to prevent the presence of anomalies and failures in our compute node, which are the core of a data center. But on the other hand, we also have to take in consideration a reduction of the PUE in our data center. So we have to, the PUE is an index that tells us how we can are good to save energy in our data center. And in principle, if we are able to reduce this PUE parameter, we are able to save energy. And if we come back to the beginning of this presentation, we see how reduce the energy consumption of data center is very important for all the data processing system. And this is for sure have an impact on many different fields in which a data center could be very, very useful. So I give you a very brief introduction of our use case, because in the next presentation we can go more on detail. So I can leave the floor to my colleagues, and I'm happy to take question in the next section.
Thank you very much, Matteo. Again, for people attending the webinar, feel free to post your questions or your comments there. I think this was a very good introduction. One of the reasons why we are organizing this webinar is for sure to create awareness about the work we are doing in the project, but we think that many of the people in this community may share the same problems and the same challenges. So I can imagine a lot of data centers are part of HIPEAC. Also, maybe some of the people from outside HIPEAC are connected now to the webinar and having similar challenges. So what we would like is also that you contact us, because we have a lot of activities in the project also to discuss and to exchange views with other people. I think it would be very interesting to know the way other communities are solving these kind of challenges, to see if you are really using graphs for this, if not, and maybe you may be users of the technologies we are developing here, or at least we could run also some benchmarks to understand how to compare the different solutions and their performance. But without further delay, I would like to introduce here our next colleagues, which are Matteo and Junaida. They will go deeper into this use case. They are from University of Bologna, working directly with Cineca in this use case. And I think that you will guide us through additional content, but also you will make a demo to all of us. So we are really looking forward to that. Thanks a lot. Martin, the floor is yours.
Can you hear me okay? Can you see my screen? Is everything okay?
Everything
Perfect.
is okay.
Thank you. Thank you, Nuria. Thank you, Matteo. So I will talk a little bit more about the technical progress we have already made addressing the use case 4, meaning the graph processing for sustainable HPC operations. And then Junaid will present the hands-on demo of our anomaly anticipation system that uses graph neural networks. Okay, so we've talked already. The Graph-Massivizer has been briefly presented as a concept, but let's just refresh it a little bit, and then I will talk about how the Graph-Massivizer infrastructure actually translates to what we are doing in the context of use case 4 for graph digital twin. Okay, so the idea of Graph-Massivizer is that we want to process massive data, which we are transforming into a graph. We want to do some processing on said graph to generate some insights. Of course, this processing we want to do, as Reza said, we want to do it with regards to energy efficiency, compute optimizations, and optimal utilization of resources. So this is the whole idea. So let's look at how this translates into the use case for graph processing for HPC. Okay, so this is the diagram of the, I don't know if you can see my mouse, but okay. This is the diagram of Graph-Massivizer.
You see the mouse, Martin.
You see the mouse?
Yeah.
Oh, okay, perfect. We have the inception of data by the graph inceptor, transformation into the graph. We have all the processing that is happening on the graph, happening on the graph scrutinizer. And then we have this optimization layer, which makes sure that that our processing is computationally efficient, energy efficient, and utilizing the optimal resources. So what does graph inceptor and graph ingestion layer mean for our use case? So the main point is, as Matteo has said, we want to integrate with the monitoring framework. HPCs are an extremely complicated machine, and they require a robust monitoring framework that is able to ingest the huge quantities of data these machines are producing. So we have already developed and deployed this monitoring framework. Now we want to integrate the graph inceptor with this monitoring framework so that the streams of data coming from that monitoring framework can be in a real time transformed into a graph and then passed on to graph processing task. Specifically, we want to have integration of 3 different data streams. We have historic data sets which we store on the local database. We have publicly available data, which we are periodically exporting in the form of Parquet files. But more importantly, we want to be able to have real-time integration. So the data collected by Examon is collected in the form of MQTT streams, and we are aiming to integrate these streams directly into the graph inceptor, which means that we can create real-time graphs and run, for instance, inference of our graph neural networks, or do any sort of basic graph operations that we are particularly interested in. Okay. So all our graph operations are happening in the graph scrutinizer. These graph operations we call BGOs. These are basic graph operations, and we have a couple of them. Of course, for our use case, we are particularly interested in machine learning applications. Specifically, we will more in detail talk about anomaly anticipation using graph neural networks. So this would fall into the category of detective and predictive models. Here we have anomaly detection, anomaly anticipation, energy consumption prediction, thermal predictions, and so on. Then we have what we call descriptive models, which take as an input either tabular data or graph, and they're creating a data-driven graph which generates some sort of descriptions about our time traces. So this can be, for instance, a causality map of the input data that we are observing. And of course, then we have the most basic BGO, which are graph queries. So graph queries are able to allow the end user much easier insight into this really complex data. Because, of course, we already have the capability of using queries on Examon, but Examon is a SQL database, which means that you need to have a lot of domain knowledge about how the data is actually structured to extract any sort of valuable information. With Graph Query, we can have that, we can integrate that in a much more user-friendly way. And of course, we want to have the Graph Query serve the real-time data. This is why we need the integration with MQTT Stream and Examon. Okay, of course, we want to do that, as I've said, in an optimal green and computationally and resource aware way. This is why we have Graph Optimizer, Greenifier, and Choreographer. I will not talk more about this because it was already covered by Risa's presentation, but should you have any questions, we can come back to these parts of the presentations. Okay, so as Matteo said, we have a couple of different objectives when it comes to this energy efficient and green digital twin of the supercomputer. So when it comes to energy efficiency, there are a bunch of things that come into our head, right? Energy efficiency, of course, means that we reduce the we improve the PUE, we decrease the energy consumption that you need for certain computations. But energy efficiency also means maximum utilization, meaning that since we already have the hardware, we want to take as much advantage of it as possible. This means that we want to be reducing downtime and increasing availabilities. And our past work together with Cineca has already been focused on that. We were working on anomaly detection. But why we were so interested in the prospect of graphs and graph processing is because we finally saw a way that we can transition from anomaly detection to anomaly anticipation. And this is what graphs allows us to do. So in this part of the presentation, I will focus on the first sort of result of our green data center methodologies, which is increasing availability through anomaly anticipation. Okay, so as Matteo has already said, the point is that we want to integrate a bunch of things. So we have the Examon framework that is serving us the data. We have then the graph injector, which is and Graph-Massivizer toolkit that is transforming this data into the graph formats. And then we have the actual applications, in this case, graph neural networks, which are running inference. Then we are feeding that back into the Examon graphical interfaces, where we are serving this information to the end users through the visual data twin, which is, this is the, on the picture here and here, these are 3D renders of a digital twin, where we simply see the green lights for the nodes means that everything is okay, and the red lights means that there is some probability for the anomaly. Okay. So what exactly are we doing? As I've said before, increasing availability has been our research focus for quite some time, of course, motivated by our close collaboration with Cineca. And in the past, the best we could do was semi-supervised or unsupervised anomaly detection, which just means that we were able to detect in the real time if the node is operating according to expectations, or is it experiencing some problems, which means that if there were some problems of the node, the response of the system administrator was faster. Okay, but of course, we were doing that from a perspective of semi-supervised and unsupervised learning. Why weren't we doing that from a perspective of supervised learning? Well, I mean, the answer is very simple. Supercomputers are already very reliable machines, which is of course great for us, but that means that from a machine learning perspective, this is a more difficult problem. Why? Because we have orders and orders of magnitude more data about normal operation than we have about anomalies. That means that you cannot really train a supervised learning algorithm because the classes are simply too unbalanced. Normal operational data represents more than 99.9% of all the data points that we are collecting. So this is why we had to resort to self-supervised learning. However, our intuition was simple. If we include additional information, encode it in the form of a graph structure, then maybe we could pose the problem of anomaly detection and prediction as a supervised problem. Because obviously, if you want to do prediction, you have to do supervised problem. And graphs were a tool that allows us to make this jump. So what did we do? Our assumption was that, of course, the nodes are organized in a physical compute room in compute racks. So we represent each compute rack as a line graph, where each node is connected, when each node is represented as a vertex in a graph and connected to the node above, directly above and directly below. Then we train a graph convolutional network aimed at predicting whether or not the node will experience an anomaly in a designated future window. So what are the preliminary results? We tested this information on a couple of racks. We are still conducting more conclusive and more comprehensive tests, but the point is that we are already achieving very promising results. We are, for up to 24 hours in advance, we are outperforming the previous state of the art for anomaly detection. So by transitioning to graphs and supervised learning, we can have similar prediction, similar performance that we had just for anomaly detection, now for prediction up to 24 hours in advance, which of course is a result that we are extremely happy with. How are we? This is the performance of the previous state of the art, which is anomaly detection. So we see that up to 24 hours in advance, we are outperforming it. How are we deploying the model? The model, as also Junaid will show, are deployed by having a bunch of models trained on different future windows running concurrently and producing diagrams like this, which essentially which give some graphical information to the end user about the probability of anomaly in the future windows. So larger models with larger future windows, up to, for instance, 3 days in advance, are less accurate, but of course they give you more. They give you a higher future window. The models with lower future windows have much higher accuracy, but of course they have slower future windows. So this is sort of the trade-off, but we communicate everything to the end user. Okay. So conclusions, I just want to impart this point. We are extremely happy that graphs, we identify a use case where graph really unlock a capability that was previously inaccessible to us. So this is why we're excited to be part of the project that is unlocking and bringing graphs to the data centers. Okay, now let's go to the tool. Now let's go to the demo of Junaid, where we will show how we are creating the graphs and how we are running the inference, and also how you can play with the models that will soon be released, with the code that will soon be released as part of the Graph-Massivizer project. Thank you. Now, Junaid, please, I don't know if you will do the video or if you prefer to do the demo, if you prefer to do the live demo. Stop sharing.
Hi, everyone. My name is Junaid. Since we are short in time, so I will just start to share the video. Please let me know if you can see the screen.
Yeah, we can see it.
So I started the video. Hello everybody, my name is Junaid Ahmad Khan and I will be giving a short demonstration. In this demonstration, I will be showing an example of creating a graph which is suitable for machine learning and then passing it into a graph convolutional model which gives an output which is the probability of an approaching anomaly. For this, I will be using the PyTorch framework and the library PyTorch Geometric, which allows for graph processing. I will be using pandas and NumPy and the other standard big data tools. After this, I will be using visualization methods such as heat maps to show our model's performance. So let's start. I already ran all of the cells in the notebook to save us some time. With this command, we installed the PyTorch Geometric library. Here I load all of the relevant libraries that I will be using for my demonstration. Here I show all of the future windows that we selected, ranging from 1 hour ahead to 72 hours ahead. Each future window has a separate model of its own. In this cell, I set up the device for our environment. Here I download the relevant data for the rack number 12 from the open dataset from Chineka. These Parquet files are the data for each of the nodes in the rack number 12. In this cell, I am showing the helper functions that I will be using for my demonstration, such as reading file function, new label creation function, which is used for creating the new label for anomaly, the feature extraction, label extraction functions, and here this is the structure of the model for anomaly anticipation. In this model, I have 3 graph convolutional layers followed by 2 dense layers, which gives the final output which gives the final output of one feature, which is the output of the anomaly. For this demonstration, I use the FW of 4 and the index 200. This is arbitrary. Any other values could have been used. In this cell, I read all of the Parquet files for the rack, concatenate them into a single object called data, and then transform using min-max scaler to get a final data frame of shape 18 rows and 418 columns, where 18 is the number of rows in the number of nodes in the rack. This is the creation of the edges for the graphs. The strategy that I used is each node is connected to the node above and below. This is the final data frame where rows are the nodes and the columns are the features. On this data frame, I run the function of feature extraction and label extraction to create a final object, PyTorch geometric object called data. These are, as you can see, this is a graph where these are the features and these are the adjacency metrics, the edges, and these are the labels. Afterwards, I create this model as I explained before. Then I load an already pre-trained model for the FW4. I pass the graph that I created into this model, use the sigmoid function to get the probabilities, and here we can see the results of the output in a data frame where one column is the true label and the other is the predictions. As all of the true classes are 0 in this data that I created, in this graph that I created, so as you can see, the predictions are extremely low. Let's now move on to the second part, which is visualization. Here in this cell, I load all of the pre-processed data for each of the feature classifiers. Here I load all of these files in this cell, and then I do pre-processing from these files to get the relevant data for the node 1 of this rack, which is 240. Here I read the 240 rack node of the rack number 12 to get the true labels, and then I append all of these probabilities and the true labels that I extracted into a data frame called df heat, and df heat can be seen here. These are all of the classifiers, and then we see the visualization in the form of heat maps. Here at this point we have an anomaly, and we can see from the heat map that the classifier of feature window 4 can be seen to show that that there is an approaching anomaly. This can be further seen in another heat map that I created, where I included other feature classifiers. This is the anomaly, and we can see that in this heat map it is more brighter closer to the anomaly, so we can see which shows that the models are showing signs of predicting, which leads to the final heat map, which includes all of the classifiers. At the very right hand corner we have the real anomaly, and as expected, this this portion near the this part of the graph near the anomaly, the figure is extremely bright, showing that each of the classifiers are more dense here, and showing that the models are behaving as they are supposed to have been behaving, which is predicting the approaching anomaly. Thank you, and if you have any questions, please feel free to ask. So that's about it. Sorry if we went 1 minute ahead.
No problem.
Thank you.
I mean, it's still perfect. Thank you very much. And I don't know if it was easy for people attending today to follow the full webinar. Probably you need to have good knowledge to understand the full demo. But basically with this, we show that the project is not only going to advance scientific challenges, but also we are very practical in the sense of bringing demos quite early in the project and also addressing real problems that our companies and organizations have, as I mentioned in the beginning, in terms of economic nature, but also from a more societal point of view. So I think that this one shows very concrete results of the project. And now we go to a funnier part, I would say, and I will invite Radu again, because this is just an example of one of the use cases we have developed in the project. Thanks again to the colleagues Mateo, Martin, and Unai for the preparation of the webinar and these interesting presentations and the demo. But I think that the project also expands around different sectors and problems, and this is what we will tackle now in the panel discussion. No, Radu, we will bring the representatives of the other use cases in the project so that people get a better flavor of what graphs can do in order to solve all these challenges. You will see that there is a wide variety of them. So Radu, I give you the floor again so that you moderate the panel discussion, and we will learn more about the other use cases and how Graph-Massivizer is contributing to them.
Yeah, thank you, Nuria. So I will moderate the discussion on the use cases. So we saw the supercomputing exascale use case. Again, we are a systems project, so everything, it's in the first year, and all our demonstrations so far are very, technical and back-end oriented. But now let's go on with the other use cases. So panelists, kind of your quota is 2 to 3 minutes per intervention. So I will start with the first use case of Peracton, Ireland, Laurențiu Vasiliu. I think you are CEO or CTO. I don't know exactly what you are, but please introduce. Yeah. And the question is for all of you, what is your use case in 1 minute in simple words, and why graph processing at massive scale is relevant for you? Why are you in the project?
Right. So I'll start. Our company deals with design modeling of financial algorithms. So we have a dedicated environment to test financial algorithms for investment and trading. And we do this for us and also for our clients. And one of the problems is always the data. And the more advanced models we have in the financial algorithms, including machine learning and other AI technologies, the more data we have. And this data is not necessarily always available, always complete, and for the length and duration we want. And there are, again, a lot of other problems with historic data. That very old data is not relevant for the current types of markets. And therefore, a solution is using synthetic data. But then synthetic data can be created in various ways, but not necessarily in very big quantities. And then there is the problem of the quality of synthetic data. That is yet another aspect to be very carefully designed. So what Graph-Massivizer does for us is that will enable us to produce synthetic data in extreme quantities, and it will be available for us to fine-tune the quality we want and control it. And in this way, we can pre-test a lot more the financial algorithms we're designing before going live on financial markets with money. So this is in a nutshell what we do.
Say something about the green part. Okay, no, this will be the last question. Sorry. So let's move on to event registry. So Gregor Leban, you are CEO, CTO. What are you?
CEO, yeah. Yeah, so our company is basically a media intelligence company. So what we do is we collect news that's published online every day in real time. And our goal is basically to extract from the news as much structured information as possible. So one thing that we try to do is we want to try to extract specific relations which are mentioned in the news articles, relations such as, let's say, product launches, acquisitions and mergers of companies, maybe hiring, layoffs, launching of new products, things like that. And for each of these relations that we extract, we kind of extract additional semantic information, like what happened with whom, where, when, so who is involved in this relation and so on. So all this information basically has a lot of semantic information. And that's also exactly the reason why Graph-Massivizer makes sense. So all this data that we collect can be somehow represented as a graph. And this graph we want to mine to basically find things like specific trends that are happening, maybe potentially anomalies in the data, and especially predicting potential future events. So if you see that a certain thing is happening or certain relations are happening with a particular company, what you want to do is you want to predict what could be the potential following events based on the previously extracted data. That would be very brief.
Thank you, Gregor. And the last, not the least, yeah, it's a big Robert Bosch, yeah, from Germany, on automotive industry. So why do you need graph processing at scale? Muhammad Gal Elram, please.
Yeah. So yeah, I'm not like others, a CTO or CEO, just a research engineer. So to talk about Bosch, Bosch is a huge company, like with a long history, with many plans for manufacturing. And this motivated at some point moving for Industry 4.0, okay? And to achieve Industry 4.0, you need to integrate your data into a homogeneous data structure. And here comes graphs, okay? So once you get everything in the graph and you start building the graph and you exceed few millions of entities, then the graph is huge. It is really hard to apply any algorithms and so on it to get any value. So our target is to get like values that can help us in optimizing the manufacturing, optimizing the processes we have, and like apply that in different locations. Okay. So once you build a big graph, it started to get like more costly. We have to spend a lot of money to process it. We also produce a lot of use a lot of energy. Okay, so we have to control that. So here comes Graph-Massivizer when we would like to use it, like, and to develop with our partners something that can estimate the cost, estimate the the impact on the energy and so on. Yeah, and optimize these for sure.
Hey, thank you for the introduction of the use case. I think all of us should have now a more concrete overview of the spectrum. We have 4 use cases, all of them with kind of different requirements and characteristics. Yeah, finance, social news, and political, manufacturing, and supercomputing. Now, I would like to challenge you with the next question. You know, we are an extreme data processing project. So kind of the thing I expect if I see an extreme data process is how you reduce extreme data to knowledge. Yeah, you are overwhelmed by data. We have too much data. We don't know how to cope with data. And there is concept of dark data, dangerous data. So we have to eliminate data. Yeah, but at the same time, we said, okay, we need synthetic data. We saw Laurențiu, you know, saying that. So I find it, when I wrote the proposal, you know, together with you, I find it as a contradiction somehow and very funny. You know, on the one hand, we have too much data. On the other hand, we have to generate more data, synthetic data. So
yes, so we are practically we want to generate more data because that's a market problem that we have, and we are going somehow in the opposite direction as the other use cases. But this is again about the testing and extra testing of the models we have. And roughly, I'm going to give an example for financial commodities that are, for example, wheat, various grains, and so on. Relevant data for testing is about 10 years with these conditions available every minute of every second. To stress test a model, 10 years is not enough because we just capture a fraction of behaviors. Their synthetic data comes into place where we could generate equivalent of 100 years or 500 years of data, and then we test. And these are extreme volumes. And these extreme volumes cannot be generated, in a ad hoc manner or kind of a hacked approach. We need a solid scientific base, and their graphs are coming into place because we have the template of historic data that is out there. We capture in the graph structure practically the statistic properties of this data. And then we will generate new types of data, but we still keep the patterns and statistical properties we identified originally in the historic data. And practically, our algorithms are going to see a lot more unknown situations and challenges, and therefore they're going to adapt better, or we are going to change them to be more agile. So this would be practically the role, and that's why we need so much more data.
What about the other use cases? Bosch, is synthetic data relevant for your use case?
Yes, synthetic data is will remain relevant for a couple of reasons. The first reason is privacy. Okay, so we cannot, our tools or our, let's say, our manufacturing data comes from us and for our customers, such as these are big customers like Daimler, Audi, and all of these people. And we should not really disclose their manufacturing statistics or something like that. And this is have a lot of value for them, even if we are the one who are performing this or even selling the products. So we need to synthesize data to be able to do first research, simulate another thing, simulate scenarios also, and control the simulation of different scenarios. And to be able to also let's say, overcome some biases in the data. So success is always there. However, you need also to simulate and to be able to deal with failures, which is rare, okay, compared with the data coming in successful. So it also helps us overcome some biases.
Yeah, so if I understand both of you correctly and put everything over one single hat, the problem is with data quality. We are overwhelmed by low quality data. Yeah. And low quality data can introduce biases, can introduce risks, can introduce security leaks, and all sorts of other, unfortunate outcomes to our training algorithms. Gregor, Matteo, what about your use cases? Do you have relevance scenario in using synthetic data, or are you dealing only with high quality data sufficient for your analytics?
Yeah, so in our case, we don't rely on the synthetic data because, first of all, we have enough of the real data. So since we collect in the range of 1 million articles per day, it's not that we kind of lack the data. And since we also have historical data, so in our case, we have data going back to 2014. Maybe it's not like in the Laurentio's use case, where 10 years of data is not enough. In our case, usually it is enough. What you want to do is you want to have a big enough time window of data so that you kind of capture different types of things that happen in the world. So if you would, for example, just look at the data, during the COVID, then things would be very biased because during COVID, everything was kind of very anomalous. So what you want to do is you want to have a time window that goes beyond such specific time periods. But in general, it's not so important for us to have 100 years of data, because probably the relevant things are still what's happening relatively now and not so much like what happened 20 years ago.
But you are dealing with news data, so collected from social media, and we know nowadays trendy habit is to, fake news and conspiracy theories. So aren't you prone to such attack of, low quality, malicious data, news data?
So the thing there is that we do have this redundancy. So when you extract specific relations from articles, what you want to do ideally is you want to find the same kind of relation also found in other articles. So you have kind of a redundancy where different sources are covering the same event. And in such cases, you have this as a kind of a more reliable information compared to if you just have something reported by one source. I think that's one thing that we need to keep also on our side is that we need to make sure which sources we cover. And in this case, we just make sure that we don't ingest sources which generate fake news or content which is unreliable. And this is not so difficult. I mean, you just don't go to social media, you just go to the news, which has big enough number of viewers and they're long enough online, and you hope that it's good enough.
Okay, so you are restricting yourself to trustworthy sources of information.
Exactly.
Where you verify, the source of the data generation. Good. Let me move now to the last question that I prepared for you. Of course, people online are free to ask questions, and we got a question. So the last question is about, the impact. In European project, impact is important. Over the years, we used to restrict ourselves on economic impact. Then we kind of move on at the social level. Yeah, social impact became more and more important. And nowadays, environmental impact is becoming of primary concern. Altogether, we call it sustainability. I would like you, the panelists, to focus on the social and environmental impact on your use case. And I will start with Cineka this time. And Matteo, please also check the chat because there is a question for you, which relates to what I said. Please read the question and maybe you try to answer. If you need some time of thinking, I can move to the other panelists.
Yeah, I thought that maybe you can go through the last question, Radwan. Since we have a couple of questions there, I invite the colleagues to go through them, and maybe you can also take orally the questions after this round.
But this is the questions to sustainability relates.
Yeah.
Nuria. So basically, Koen de Boscher, sorry for pronunciation, says, I fail to see how a 6 megawatt supercomputer can get green. 6 megawatt electric power emits 2.2 tons of CO2 per hour. This is 50 tons per day, 20,000 tons per year, and it continues with all sorts of negative connotations.
So basically, he is arguing if we may claim that it's efficient, but furthermore, if we could claim that this is sustainable, taking into consideration that even if we save, still there will be a high consumption. So I don't know if the colleagues from Cineka or University of Bologna may want to take this one. Will graph processing be sustainable in this context?
I mean, there are a few points here, and please, Matteo, add something if I fail to answer it. But from our perspective, right, the computations that we are doing, we would have to run them somewhere. We are not, Cineka HPC machines are not used to mine Bitcoin, but they're used to do processing for astrophysics, for Eurofusion projects, for drug discovery, and stuff that is critical for humanity as a whole. And this research has to be done somewhere. So now the question is not whether or not we do it. We have to do it, but the question is where we are doing it done in the most optimal way. And from this perspective, doing it in a supercomputer like Leonardo, which is built from the ground up with sustainability in practice, and adding these practices that we talked about, which is green scheduling, maximizing availability, all these stuffs, this means that the processing that should have been done is done in the most green and most sustainable way possible. So yes, of course, we are using burning electricity to do this, but in any other way, we would probably be burning even more electricity and energy. So from this perspective, yes, we believe that it is sustainable.
So Koen, I don't know if with this we have answered your question. feel free to put more comments in the chat if that is not the case. There's another one for Gregor, so maybe Gregor, you may want to go to that one now. So are you going through a list of sanitized institutions, and how does the arbitration of truth takes place?
We are not the ones deciding what's true and not. So what we have is basically a list of sources that we cover and ingest, and that's what we process. And in these cases, what we do is we make sure that the sources that we process are the sources which otherwise are popular online. They tend to generate what's known as high quality content. And it's not us who basically decides this is fake news and this is not. So this is not something that we can do. In general, we just ingest content from all the sources that we can get, and then the user who has the access to this data can then decide which sources to ignore and which not, because each event that we detect is then associated with a source of information. You can then say which kind of sources you want to trust and which not.
Laurenzi, what about you? When we discussed about your use case, we said, financial people are all, ruthless people, caring about money and nothing else. So why should we fund
Oh my God, that is not a very politically correct comment for a webinar.
Well, I put the quotes, and the smiley.
Yeah, so there are several aspects to look at. So first, let's go back to generating this quantity of synthetic data. So indeed, there is energy involved in producing it and processing all these graphs and data. So there are two ways to control and minimize what's going on. So first, we do have this Graph-Massivizer component into the platform that we are developing, and we want to monitor accurately how much energy will be spent for generating, synthetic data volumes per very specific units, and we'll try to optimize and minimize this thanks to this component. The second part would be once this platform is ready to be deployed, we would deploy in the cloud. We work, for example, with a company, with a cloud provider that explicitly shows sources of green energy that are fed into the servers. So that's a second part, that we would deploy such a technology on servers that are using green energy, solar and wind. So that's on the infrastructure. On usage, so these algorithms for investment and trading, so I don't know, many of you may have heard of ESG. These are some factors that are attached to financial data, where companies are describing various elements that can be quantified, and in this way their green impact and social and ethical and governance can be measured. So our models can easily take into account such factors, and not only this, we can also take into account the importance we can give to these factors, because it's not necessarily true if an oil company says that has a very strong green policy, that in reality this is happening. So we can also adjust our models to take into account the reality. But then this is the green algorithms practically are looking to invest, but to concentrate capital in the companies that are most green and most environment aware. So it's a kind of a redistribution of investment from various sources that will be done by these algorithms. So that will be practically the effective approach we would have with investing in green with our algorithms.
Thank you, Laurenzi. Very convincing. And Mohammed, now we talk about Bosch, a big, highly successful company. What is the social worry of Bosch regarding your use case?
So maybe I will focus on the manufacturing, okay, and also on Bosch. So Bosch was part of the company that really committed to reducing or being actually neutral in the CO2 emissions and so. And I would really highlight something. So we would like to use the huge processing or processing of knowledge graphs to achieve this target, not to make it worse, okay? And even in software, it is sometimes the failures of runs of a specific algorithm are the problem. So you run several times, debug several times, to reach the correct computation, let's say, correct parameters or something like that. And this is for us is a problem, because now you run your servers for long hours just to find the correct way or the correct resources. Okay, so from Graph-Massivizer, we hope to solve such problems, to be from first sight, know how much resources are needed, make them to the minimum, and minimize them, and use the only required one. Okay, yeah, this is really important. It is not about like scaling up, but scaling up wisely, not to spoil our like CO2 targets or neutrality targets. Yeah.
Thank you, Mohammed. This closes my intervention of the panel. If there are any other questions on the chat, please free to ask. We have still 4 minutes left. Otherwise, I give the last word to Nuria. Thanks, everybody.
Thank you very much, Radu. Still use the chat facility or the question and answer if you want to make a final question. Our colleagues will be here. Meanwhile, let me share my screen so that just a moment, just to give you some final information before we close the webinar. So we would like to invite you to one of the big events we are organizing. We will have our second Graph-Massivizer workshop on serverless, stream scale, and sustainable graph processing systems in May 2024. That will happen in London, South Kensington, in the context of the International Conference on Performance Engineering. We are working already hard for this, and there are some important dates that I would like to highlight here in case you are interested in submitting papers and you are attracted by these technologies. So January 22nd of the next year, so just after Christmas holidays, will be the deadline for submissions. Then in February, we will notify the selected papers, and people will have the opportunity to present the papers in London. I think this is an opportunity, first of all, to submit interesting papers to help us know about the work that you are doing, but also, even if you are not submitting papers, if you are interested in coming here, I think you will learn a lot, not only about what Graph-Massivizer is doing, but also about other initiatives. And I think that this can be quite relevant in order to advance on some of the challenges that my colleague Radu mentioned at the very beginning of the webinar. So please pencil your agendas and keep in touch with us if you're interested in coming or you have any question. Then I think it would be quite good, again, if you are interested in graph processing, and especially if you are already working on that you follow our channels. So here you have the link to the Graph-Massivizer website that I also put in the chat, where you can find information about the project, but furthermore, you will find interesting information about the 4 use cases that have been introduced today, and also the different software tools. As Radu presented in the beginning, we are providing a platform that is composed of a number of tools. Many of them can be used also without the support from the others, and most of them will be open source. So I really would like you to stay tuned on that, because basically what we are doing is creating tools and technologies that may be used by the others. So this should be a very open project so that all people can benefit from these technologies. And you've seen already quite impressive results that have been achieved after 1 year of the project, because we've been executing the project only in 2023, and still there are 2 years ahead of us. Then follow us also in LinkedIn, in Twitter, and YouTube. We have channels in all these social media, but in LinkedIn we are particularly active. Just a reminder that all the presentations and the recorded version of the webinar will be available through our website. So go there and also check the information. And it may probably be published through the HIPEAC website. In any case, stay tuned and we will provide all this information. With that, I would like to say thank you, first of all, to HIPEAC again for giving us the opportunity to organize this webinar in the context of this community, and also to all my colleagues that have been really wise, and I'm very efficient in preparing the presentations and keep the timing under control. You will get also a couple of questions now before leaving the webinar, where you will be asked about the expectations about the webinar. Please don't leave without answering them, because I think it will be a learning experience for us, and we will be able to do it better next time. And with these final words, I would like to say thank you again to all of you. I wish you a very nice afternoon. Stay tuned, and thanks again for your time today.
Everybody.
Thanks a lot.
Thank you.
The webinar
Thank you.
Thank you.
Thank you.
Yeah, thank you all.
Have a good afternoon. Thank you very much to all of you.
Thank you.
Did you get the questions? Because I didn't get them myself.
Yeah.
Yeah.
Ciao.
Okay.